Welcome to this brand new JavaFX project, a fully animated 3D solar system built completely from scratch. In this video, we'll create orbiting planets, add realistic lighting, make the sun glow, and bring the entire system to life using pure Java code. If you enjoy creative coding and modern Java projects, you're going to love this one. Let's get started. Inside your JavaFX Maven project, create a brand new Java class and name it Solar System 3D. Now before we start building the actual solar system, we need to add all the required JavaFX imports. We begin with AnimationTimer. This is one of the core pieces of JavaFX that makes real-time animation possible. AnimationTimer allows us to update the positions of the planets every single frame, usually 60 times per second. Next, we import the application class, which is the foundation of every JavaFX program. Along with that, we also import the static launch method, which we'll use to actually run the project. Moving on, we start bringing in all the essential classes needed for rendering 3D objects. We import scene and the entire JavaFX scene package because this is where most of the 3D engine lives. This includes groups, nodes, the camera, and every object we'll place into the 3D world. JavaFX's scene graph works like a tree, and everything we create, the sun, the planets, the labels, will be placed inside this graph. Next, we import color and PhongMaterial. PhongMaterial is especially important for 3D graphics, because it allows us to apply colors, textures, highlights, and realistic lighting to our 3D spheres. We also import point light and ambient light. Lighting is one of the most important parts of 3D graphics, because it controls how objects look on screen. Point light simulates a light bulb. In our case, it will act as the sun's illumination, casting highlights and shadows on each planet as they orbit. Ambient light gives us general, low-level brightness across the scene, so the dark side of the planets isn't completely black. Next, we import the rotate transform. This helps us adjust the orientation of our camera and other objects. We then import stage and scene anti-aliasing. Stage is the main window of the application, the container that holds everything we render. Scene anti-aliasing is a very important detail, it smooths out jagged edges in 3D graphics. Finally, we import the font and text classes. These are used to display labels for each planet. Instead of leaving viewers guessing which planet is which, we'll attach a small text label that moves along with each sphere. So as the planets orbit, the labels follow them smoothly, always readable from the main camera angle. Now we'll set up the main structure of our program. Solar System 3D class extend the JavaFX application class. By extending application, we gain access to the special start method. This is where JavaFX builds the window, sets up the 3D scene, the camera, the sun, and all of our planets. So go ahead and implement the override start method, and we'll begin placing everything inside it step by step. Next, we'll define two constants for the size of our window. We'll set the width to 1280 and the height to 720. These values give us a clean, widescreen aspect ratio that works great for 3D graphics. Now we'll create a static inner class called Planet3D. This class represents a single planet in our solar system, and it holds everything we need to animate it. We start with a 3D sphere, which is the actual planet you'll see on the screen, and a text label that follows it. Next we define three important values: the radius, which controls how far the planet orbits from the sun; the speed, which determines how fast it travels; and the size, which sets the physical scale of the sphere. Finally, we include an angle value, which updates every frame and drives the planet's orbit around the sun. Now let's move into the constructor for our Planet3D class. This is where each planet gets all of its key properties and becomes a fully functional part of our solar system. We start by passing in the planet's name, its orbit radius, its size, the time it takes to complete one full orbit, the color of the planet, and the group we're adding it to. Each of these values plays an important role in how the planet behaves and appears in the final animation. The first thing we do is store the radius. This number controls how far the planet sits from the Sun and determines the size of its orbital path. Next, we assign the size, which sets the radius of the sphere that represents the planet visually in 3D space. After that, we calculate the planet's speed. Instead of manually specifying a speed value, we convert the orbit time into an angular velocity using the formula 2π divided by the number of seconds in a full orbit. This gives us smooth orbital motion that feels natural and perfectly synced. With those values set, the rest of the constructor will create the 3D sphere, apply its material and color, position it on its orbit, attach the label, and then add everything into the world group. So this constructor essentially takes all the basic information about a planet and transforms it into a living, moving object in our 3D solar system. Next, we create the actual 3D sphere that will represent our planet in the scene. We pass the size value directly into the sphere constructor, which sets the radius of the planet in 3D space. Then we build a new PhongMaterial, which controls how light interacts with the surface. We start by applying the planet's diffuse color. This is the main shade you'll see. After that, we set a white specular color. Specular lighting gives the planet a subtle highlight whenever the sun's light hits it, making the sphere look smooth, round, and more realistic. Finally, we attach this material to the sphere, completing the visual appearance of the planet before it's added into the world. Now let's create the label that will appear next to each planet. We start by building a new text object and passing in the planet's name. This makes it easy for viewers to recognize each planet instantly. Next, we set the label's fill color to white, which gives a strong contrast against the dark space background and keeps the text clean and readable from any angle. After that, we choose a simple sans serif font at size 14. This keeps the label small enough not to distract from the planets, but clear enough to identify each one as it moves around the Sun. With this label created, we'll soon attach it to the world and update its position so it follows the planet smoothly during orbit. Next, we position the planet inside the 3D world. By default, every sphere starts at the center of the scene, which is the exact location of our Sun. So to place the planet on its orbital path, we shift it outward along the x-axis using the radius value we stored earlier. This sets the initial distance from the Sun and defines where the orbit begins. We keep the y position at 0 so all planets stay on the same orbital plane, and we set the z position to 0 for the same reason. This creates a clean top-down orbit layout, and later on, as the angle updates, the planet will move around the Sun in a perfect circular path. Now we need to position the label so it sits nicely next to the planet. We start by shifting the label along the x-axis using radius plus size plus a small offset. This places the text just a little to the right of the planet's surface, keeping it readable without overlapping the sphere. Next, we adjust the y position by moving it slightly upward using the planet's size. This keeps the label floating above the planet instead of sitting directly across its center. Finally, we leave the z position at 0 so the label stays on the same depth plane as the orbit. As the planet moves, we'll update these positions so the label smoothly follows it around the Sun. Finally, we add both the planet and its label into the world group. This makes them part of our 3D scene, ready to be rendered and animated along with the rest of the solar system. Next, we create the update method. This runs every frame and is responsible for advancing the planet's orbit based on the time that has passed. Inside the update method, we begin by increasing the angle using the planet's speed multiplied by the time step. This gradually rotates the planet around the Sun at a realistic rate. Using that angle, we calculate the new x position with cosine, and the new y position with sine. Together, these two values trace out a perfect circular orbit. Every frame, the angle changes just a little bit, the x and y positions shift, and the planet smoothly travels along its path. Once the new coordinates are calculated, we update the sphere's position by setting its x and z values. This moves the planet to its new spot on the orbit for the current frame. After moving the planet, we reposition its label so it continues to follow the orbit smoothly. We shift the label slightly to the right of the planet using x plus the planet's size and a small offset, keeping it easy to read. Then we raise it slightly along the y-axis so it floats just above the sphere. Finally, we match the label's z position to the planet's z value, so both stay perfectly aligned as they move through 3D space. Inside Start Override method, now we create a world group, which will hold our sun, planets, and the entire 3D scene space. Next, we create a new perspective camera, which gives our solar system a true 3D look. We enable depth buffering by passing in true, so objects appear correctly in front of or behind one another. Then we set a very small near clip value of 0.1, allowing the camera to see objects that are close without cutting them off. We also set a far clip distance of 5000, giving us plenty of space to render every planet, even the farthest ones. Finally, we choose a field of view of 35 degrees, which gives us a natural, cinematic perspective for viewing the solar system. After configuring the camera, we need to place it in the right position to view our entire solar system. First, we move the camera back along the z-axis by 900 units. This pulls the camera away from the Sun and gives us enough distance to see all the inner planets clearly. Next, we shift the camera slightly upward by 150 units on the y-axis, lifting our viewpoint above the orbital plane. Then we set the rotation axis to the x-axis, which allows us to tilt the camera forward. Finally, we rotate it by -20 degrees. This small downward tilt creates a clean, angled view that feels natural and makes the circular orbits much easier to see. Now it's time to create the center of our entire solar system, the Sun. We start by creating a new sphere with a radius of 70. This gives us a Sun that's large enough to stand out visually, but still leaves plenty of room for the planets to orbit around it. Next, we prepare the visual material for the Sun using a PhongMaterial. Phong shading allows JavaFX to create smooth lighting, highlights, and gradients across curved surfaces, which is perfect for the glowing look we want. For the diffuse color, we choose a warm, bright yellow using the hex code FFT46B. This gives the Sun a rich golden base tone. Then we add a very soft, pale yellow as the specular color. Specular highlights simulate the bright reflection of light on a shiny surface, and in this case they help us make the Sun look like it's emitting light, rather than just being a plain flat sphere. Once those two colors are set, we apply the PhongMaterial to the sphere. At this point, the Sun now has proper lighting properties and will react to our point lights in a realistic way. After that, we position the Sun at the very center of our world. We set the x, y, and z translations to 0. Which puts the Sun directly at the origin of the 3D coordinate system. This spot becomes the anchor point for all of the planetary orbits we'll create later. And finally, we add the Sun into the world group. By placing it inside the world group, just like the planets and labels, the Sun becomes an official part of our 3D scene and will be rendered, lit, and displayed in every frame of the animation. With the Sun now in place, we have the foundation for the entire solar system, and we're ready to start adding the planets around it. Next, we create a point light to act as the Sun's illumination source. Setting its color to pure white gives us clean, natural lighting that reflects off every planet. We place this light at the exact center of the scene, the same position as the Sun's sphere, by setting its x, y, and z values to 0. With the light centered like this, it shines outward in all directions, just like a real sun, and adds realistic highlights and shading across the entire solar system. To make the scene look even more natural, we add a second light source called a fill light. Instead of using pure white, we give it a soft bluish tone, which gently brightens the darker side of each planet without overpowering the main sunlight. We position this fill light slightly above and behind the camera by moving it back along the z-axis and lifting it on the y-axis. This creates a subtle backglow that prevents the planets from becoming completely dark on the far side, giving the entire solar system a smoother, more balanced look. To finish the lighting setup, we add an ambient light to the scene. Ambient light acts like a soft, gentle glow that fills the entire space evenly. We give it a very low intensity, just 20% blue-gray, so it doesn't overpower our main lights. Its job is simply to make sure that no part of the planets becomes completely black, especially when they rotate to the far side of the Sun. This creates a smoother, more natural look across the whole solar system. After that, we create a root group that contains everything: our world group with the Sun and planets, the main sunlight, the fill light, and the ambient light. By placing all of these into a single root node, JavaFX can render the entire 3D scene as one complete structure, keeping everything organized and working together. Now that our sun and lighting system are fully in place, we're ready to bring the solar system to life by creating each of the 8 planets. All of the planets in this project are stored in a single array of planet 3D objects. So let's take a look at how each planet is defined and what these values mean. First up is Mercury. We give Mercury a radius of 130, which represents its average distance from the Sun in our scaled-down model. Because Mercury is small, we use a sphere size of 10. Its orbital time is set to 6 seconds, meaning it completes one full orbit around the Sun in 6 seconds of real time. This gives Mercury the fastest orbital speed in our simulation, matching its behavior in the real solar system. The color is a soft grayish tone, matching its rocky, cratered surface. Next is Venus. Venus is placed further out at a radius of 190 and is given a slightly larger size of 14. Its orbit time is set to 9 seconds, which slows the motion down compared to Mercury. For the color, we use a warm, dusty yellowish tone to reflect Venus's thick, cloudy atmosphere. These values give Venus a heavier, more graceful motion as it moves around the Sun. Then we create Earth. Earth's orbit radius is 250, giving it more distance and allowing it to sit comfortably in view of the camera. Its size is also 14, matching the visual scale of a medium-sized planet. We give Earth an orbit time of 12 seconds, creating a slower, natural-feeling circular path. The color is a bright blue to represent Earth's oceans and overall appearance from space. Next is Mars. Mars sits at a radius of 305 and uses a sphere size of 12. Its orbit time is 15 seconds, giving it a smooth, steady pace. The red-orange color captures the iconic surface of Mars, making it instantly recognizable. Moving on, we set up Jupiter, the largest planet in our solar system. Jupiter is placed far out at a radius of 410 and uses a much larger size of 24. This size difference visually communicates Jupiter's massive scale. Its orbit time is 20 seconds, which gives it a slow, majestic motion. The creamy beige color reflects Jupiter's swirling clouds and thick atmosphere. Then we set up Saturn. Saturn's radius is 500, and its size is 22. It orbits the Sun in 26 seconds, making it slightly slower than Jupiter. For color, we use a soft golden tone to match Saturn's natural hue. Even without rings, this subtle color choice helps Saturn stand out. Next is Uranus. Uranus sits at a radius of 570 and uses a size of 18. Its orbital time is 32 seconds, which results in a slow and steady circular path. We give Uranus a light, icy blue color to reflect its cool, frozen atmosphere. And finally, Neptune. Neptune is the farthest planet in our model, placed at a radius of 640. Its size is 18, matching Uranus closely, and its orbit time is 38 seconds, making it the slowest moving planet in the entire simulation. The deep blue color gives Neptune a strong visual identity and completes the outer edge of our solar system. Now we're ready to bring our entire solar system to life using an animation timer. The animation timer is one of the most important parts of this project because it gives us a real-time update loop that runs every single frame, usually around 60 times per second. Inside this timer, we begin by creating a variable called last, which will store the timestamp of the previous frame. When the animation starts, the first frame doesn't give us a usable time difference, so we check whether last is 0. If it is, we simply store the current time and return immediately. This step ensures that our very first update doesn't produce any strange jumps or unexpected motion. After that, we calculate the time difference, or delta time, between the current frame and the previous frame. We do this by subtracting the old timestamp from the new one, and then dividing by 1 billion to convert nanoseconds into seconds. This gives us a smooth and accurate measurement of how much real time has passed since the last update. Using delta time is extremely important. It allows every planet to orbit at a consistent speed, even if different computers run the animation at different frame rates. Whether the viewer's system is fast or slow, every orbit will move smoothly and naturally. Next, we store the current timestamp back into last, so the value is ready for the next frame. And finally, inside a simple loop, we iterate through every planet in our planets array and call its update method. Each planet receives the delta time value, updates its angle, recalculates its orbit position, and moves its label to match. Because this happens every frame, the entire solar system animates continuously, planets rotate around the sun at their own speeds, and the scene feels alive. Next, we create the main scene that will display our entire solar system. We pass in the root group, along with the window width and height we defined earlier. We also enable depth buffering by setting the third parameter to true, which is essential for proper 3D rendering. It ensures that planets correctly appear in front of or behind one another. We then turn on anti-aliasing in balanced mode to smooth out the edges of our spheres and labels, giving the whole scene a much cleaner, more polished look. After creating the scene, we attach our perspective camera to it, allowing JavaFX to render everything from the camera's point of view. Finally, we set the background fill color to a deep space blue-black, using a subtle hex value that makes the planets and the sun stand out beautifully. To finish everything off, we configure the main application window. We set the stage title to Solar System 3D, JavaFX, so viewers immediately know what the project is about. Then we attach our fully prepared scene to the stage, connecting all the planets, lighting, and camera to the window. And finally, we call Show to display the entire solar system on the screen. At this point, the animation is live, and our 3D solar system is fully running. And finally, we add our main method. Calling launch starts the JavaFX application, which triggers the start method and brings our entire 3D solar system to life. Now that all the code is complete, make sure your main class is set to Solar System 3D. This tells your project which file should launch the application. Once that's selected, go ahead and run the project. And that completes our fully animated 3D solar system built entirely in JavaFX. We created planets, added realistic lighting, built smooth orbits, and even added labels to bring everything together. If you enjoyed this project and want more creative Java tutorials like this, make sure to subscribe and drop a comment below. Your ideas help shape the next videos on this channel. Thanks for watching, and I'll see you in the next project.